Hi, everyone. Thank you for the introduction. Today, I'm excited to tell you about Concorde, our methodology for fast and accurate CPU performance modeling using a compositional fusion of analytical and machine learning techniques. This is a joint work by MIT, Google, University of Washington, and Rutgers University. Today, I'm presenting on behalf of Arash, who unfortunately couldn't join us due to the visa issue. Arash, however, I believe he's going to join us remotely via Zoom for Q&A. So what is cycle-level simulation? Cycle-level simulators are widely used in microarchitectural designs. They allow architects explore new designs, optimize existing ones, and perform various trade-off analysis without going through the lengthy process of chip design and crazy kind of simulations. And simulations has only become more important as hyperscalers like Google, Amazon, Microsoft increasingly invest in developing custom CPU architectures for their specific workloads. And now here's how a simulator like, for example, Gen5 works. It takes a program, a sequence of instructions, and a microarchitectural specifications, of course, and turns them into a long sequence of events capturing literally every interactions between instructions and CPU components, and process them one by one. Of course, because of that, they are super duper slow. And it is intuitive, right? Because simulating in this manner scales unfavorably with the number of instructions that we have. So what we want to do here, rather than simulating every microarchitectural details, our goal is to learn a higher level model that predicts performance like CPI with high accuracy, but runs blazingly faster. By the end of this talk, I'll tell you about Concorde, our compositional analytical-ML methodology for CPU performance modeling that has constant runtime, independent of the instruction sequences, and is 5 orders of magnitude faster than cycle-level simulators. And of course, prediction error is merely 2% CPI, the CPI prediction error. So let's delve into how we achieve this. Think of a cycle-level simulator as a very complex functions with a lot of interactions, and which are very hard to model. This complex function, what it does, maps input programs along with the architecture specification that we want to model to a performance metric, let's say CPI. This framing naturally lends itself to supervised learning, right? It's very easy. This function gets an input and map it to the output. And this is exactly what prior work in this space have been doing. For example, Tau and SimNet. These methods are very promising, are very encouraging. However, black box ML models operating only on the instruction sequences have several limitations. Their runtimes still scales unfavorably with the number of instructions that we want to simulate. Their ML model tries to learn all the dynamic interactions, which is a very complex system, only from the raw instruction sequences. And that makes the training very, very hard. And on top of that, modeling the performance in this way does not exploit the CPU performance modeling problem structure. And by ignoring the problem structure of this simulation, these methods require a significant amount of training data to learn all these dynamics. And of course, larger neural networks, which makes both the training and inference costly. So what was our goal? Let's review it. Our goal is to learn a higher level model of CPI. And I keep repeating this. But it is not all obvious what the input to this higher level model that we talk about is. In fact, to be honest, we have spent a lot of time thinking about this question. What should be the input to this model? And we settled on are the performance features derived from You can guess it. Analytical models. This decomposition that we created, analytical modeling on one hand, and ML prediction on the other hand, gives us the best of both worlds. Analytical models are not used by any way to predict CPI or any other performance metrics. As a result, they are extremely easy to construct and develop. They give us a first cut estimate of the throughput limits imposed by individual microarchitectural components, similar to what we have in roofline model. Oops, sorry. Then what happens? Then we have the ML models. ML model steps in. It doesn't need to operate on raw instructions anymore. It starts with performance features that already correlate relatively strong to the CPI metric. And its job is to capture higher level interactions and higher order effects. For example, the interactions between multiple bottlenecks and multiple components that the analytical models missed. So the result is Concorde, a model that runs as fast as analytical model while achieving relatively high accuracy. And we call this architecture and this methodology of modeling a system compositional analytical ML fusion. To make things concrete, we're going to focus on modeling our in-house Gem5 based cycle level trace-driven simulator. It's nothing radically different from what you all are familiar with. Just a fairly standard parameterized out-of-order core model, similar to Gem5 O3 CPU modeling, and it uses Ruby for modeling the memory system. So what you're seeing here is the front end of our simulator. Very simple, right? It has fetch, decode, rename stages. And I've highlighted the parameters that we focus on for modeling the front end. For example, branch predictor, we have the rename width, and so on and so forth. And here's the back end of our simulator. It includes the issue stage, out-of-order execution, and commit stage, and ROB. Nothing different, right? I've highlighted like some of the parameters here as well that we model in backend, like load queue size, commit width, and so on. And you can also see some of the parameters that we model for the memory system, like cache size and prefetching mechanism. So in the end, despite all this complexity that we have in the system, a CPU is really just a collection of queues. And I want you to remember that, right? Each with its own resource constraint. And our key idea is to analyze every queue in isolation and calculate what throughput it imposes, assuming everything else has infinite capacity. And that means for each resource in the CPU, we ask these questions. What would the maximum IPC be if that resource were the only bottleneck in the system? As a concrete example, let's look at how we do this for the ROB. We assume everything else is perfect, everything is infinite, a perfect front end, infinite issue width, everything is awesome. And we calculate the throughput the program could achieve in that idealized system that we are building. Focusing on one resource at a time enables relatively straightforward analysis. So how do we actually calculate the throughput induced by a single resource in isolation? Let me walk you through an example of the number of load slots, for example. It's a cap of the number of in-flight loads instruction, and it's at any point in time. Again, we assume everything else is perfect. So there is an infinite backlog of instruction. Some of them are loads, some of them are not. Now, very simple. According to the little laws, the average number of items in a stable queue is equal to the average throughput times the average latency. So we rearrange that, of course, to get the throughput of the load instructions. It's just the number of load slots divided by the average load latency. And to get the overall program throughput, we divide the load instruction throughput by the fraction of the instructions that are loaded. Very simple, right? So this figure shows the output of our analytical model. We are not yet to the ML model. This is all analytical model. For 4 different resources, and each of them is different color. The x-axis is the instruction ID, and the y-axis is the estimated IPC. Each curve here, each of these points, corresponds to the throughput bound imposed by that particular resource. Measured over here, I think it's like 400 instruction segments. The dashed block line represents the minimum throughput bound across all resources at a given window time, the 400 instructions. And in other words, if I want to kind of rephrase it, is the most constraining bottleneck at that point in time. The green light, sorry if it's a little bit not visible very well, but the green line shows the ground truth IPC from the cycle level simulator. And as you can see, the black throughput bound closely track the IPC, the ground truth trend. Even though it's not perfect, of course, it misses in some cases. And it is expected, right? Because our analytical model makes a lot of simplifying assumptions. For example, they don't model interactions between multiple bottlenecks. It's just everything in isolation. However, still these per resource throughput curves provide informative and compact features, and that captures the first order effects driving the performance. They are essentially the key performance characteristics of that particular program. That said, they are still complex time series, as you can see. And their size scales with the number of instructions. This is not what we want. What we want is to design a model that the runtime is independent of the number of instructions. So to make the performance features independent of instruction counts, we take the per resource time series and convert them to a distribution. Sure, we lose a little bit of accuracy, but stay with me. We encode each distribution using a fixed set of percentiles, gives us a compact, fixed length representation of that particular resource. And this step allows our model's input size to be independent of the instruction. And inference becomes very, very simple. And it's regardless of the instruction size that you're modeling. Now, converting a time series to a CDF, as I mentioned, is lossy. It's not lossless. But as we will see later, this performance distribution still retains enough signal. It doesn't need to be accurate. Enough signals to predict the IPC accurately. So let's put everything back together. We start with our traces, gives us a detailed instructions and memory access information. And first, we run trace analysis to extract the inputs needed for analytical modeling. This includes instruction dependencies, register, memory, so on and so forth. And branch-based prediction rate, simple order simulation, all these methods. And approximate instruction latencies. For load instructions, this involves a simple in-order cache simulations. Then we run our analytical models to generate the per resource performance distribution. Finally, we feed this distribution along with the target architecture spec into a lightweight ML model that predicts CPI. And just to emphasize, everything in this dashed line is offline. It's one-time cost. At simulation time, all we do is a forward pass through our model. It takes about 100 microseconds. So here's how we generate the Concorde's data set. We start by randomly sampling a program region from our pool of traces, which include the spec, open source, and internal workloads that we have at Google, around 5 trillion instructions. Then we randomly sample an architecture from a space of about 2 to the power of 10 power of 23. I think we haven't mentioned it here. It's a very large space. And we do this by sampling each parameter independently and random. We then run our cycle level simulator to get the ground truth CPI for each program architecture pair. And in total, we use around 800K training and 50K unseen samples for the validation. So here's how Concorde performs an unseen test set. In the middle, you can see a scatter plot. The x-axis is the CPI prediction error, and the y-axis is the ground truth CPI, which we got it from this simulator. The plots on the side, up and bottom, on the side, is the marginal distribution of CPI and the prediction error. The average CPI prediction error is around 2%, and the error distribution has a very small tail. Only 2.5% of the traces have errors greater than 10%. And all that comes with a massive speed up, 100K faster than our cycle level simulators. This figure shows the prediction error broken down by program. And the dark blue bars show the average error, and the light blue shows the 90th percentile error. While some programs are more challenging than others, the average error still stays below 4%. And the P90 is always below, I think, 9%. So Concorde enables many other interesting use cases. Here's one example. This plot, for example, shows the CPI achieved by a big core. Big core is like something that is kind of infinite resources and it's kind of ideal. Like, for example, perfect branch predictor, ROB, very large ROB size, load store, and so on and so forth. And we use this configuration as a baseline for best case performance, a reference point for understanding what each program could achieve under ideal conditions. This plot shows the CPI achieved by ARM N1 core, and the red bars here shows the CPI increase relative to what big core, ideal core provides. And the numbers on each bar indicates the percentage of increase. Programs are sorted here by this percentage increase, actually. So for example, if you're using ARM N1 core, MCF sees the largest relative CPI increase among the spec benchmark, and while XC has the smallest. But performance prediction is great, but only part of the story. Architects also want to understand why a program performs the way it does on a particular design, like ARM N1, also known as a performance attribution. A common way to do this performance attribution is through parameter ablation study. We change one parameter at a time and observe the impact on performance. For example, here I'm showing the CPI of the big core on one of our internal search workloads. If I first reduce the cache sizes, the CPI increases slightly. Then, reducing the load queue size causes a large CPI jump. Now let's reverse the order. Let's see what happens. If I shrink the load queue first, the CPI barely changes, very small. But now, reducing the cache size causes a huge jump. So depending on the order in which you make these changes, we get two completely different interpretations of the data. The left order suggests that the load queue has 9x greater impact than the caches, and the right order, on the other hand, says that the load queues hardly matters. Don't focus on that. And the performance hit is mostly due to the caches. However, the right interpretation here is none of this. The right interpretation is that the effect of cache and load queue are intertwined. A large load queue can hide latency from small caches by increasing memory parallelism, and a large cache can compensate for a small load queue by avoiding large memory stubs. It's only when both the cache and the load queue are small that we get this big performance hit. To remove the order bias, we can take the average over all possible ordering, just one slide, performance changes, which you can see in the right bar. It correctly attributes CPI increase to both the small caches and a small load queue, with a slightly higher attribution to the caches. This kind of average that we show here is Shapley value. It's a concept I think yesterday also they used it in one of this presentation. It's from cooperative game theory, and it's the only attribution that actually satisfies a set of desirable axioms. Fairness, symmetry, and more important is order independence. So I'm going to skip this slide, actually. So let's summarize. The key takeaway of our work is decomposing performance modeling into simple analytical estimates for each microarchitectural components, and then fusing them back together with a lightweight ML model to capture higher level interaction turns out to be a very powerful approach. It gives us a models that extremely fast, constant time inference that takes about 100 microseconds and highly accurate with only 2% CPI per dictionary. Thank you so much.